Right now, at this very moment, as you watch these light rays striking the magnified eye, similar tiny beams of light are entering your own eyes. Seen from the side, the protected position of the eyeball within its funnel-shaped eye socket is shown still more clearly. Note this white stalk, which is the optic nerve, and also these muscles, which move the eyeball. The eyeball itself has a white, glistening surface. Its front part bulges and forms a highly transparent window. This thick, tough outer layer is called the sclera. This transparent, bulging portion is called the cornea. Notice also the crystalline lens, which is one of the main features of the eye mechanism. The innermost layer of the eyeball is the retina, a very delicate membrane. The retina is actually a part of the optic nerve, which transmits the light impulses to our brain. The retina is the most important and complex structure in the eyeball. Magnified many hundred times, the retina is seen to consist of this complicated arrangement of rods and cones, which convert light waves into nerve impulses. Between the lens and the cornea is the aqueous humor, consisting mostly of water and a little salt. This larger space within the eye is filled with the vitreous humor or body, consisting chiefly of water with some salt and albumin. The vitreous humor is really a highly transparent jelly and plays a very important part in the act of visual adjustment. Thus, light rays entering the eye must pass in succession through first the cornea, second the aqueous humor, third the pupil, fourth the crystalline lens, and fifth the vitreous humor in order to reach their destination, the retina. First, let us realize that light rays reflected from any object radiate in all directions, and that as an object moves farther away from us, the angle between the rays that enter our eyes grows smaller and smaller. And finally, when the object has reached a distance of 15 feet or more, the rays entering our eyes are practically parallel. Now, nature has provided that parallel rays shall produce a sharp image upon the retina without any effort, and, as one may say, with the eye in a state of complete relaxation. But if a distant object approaches the eye, the angle between entering rays again grows larger. This increasing angle changes the direction of the light rays as they pass through the lens, so that the sharp image falls behind the retina. As a result, the image upon the retina tends to become blurred. This blurring causes a response or reflex within our brain, which brings about harmonious internal adjustments of all parts of the eye. This adjustment is called accommodation. Accommodation restores the sharply focused image with marvelous speed and accuracy. This is all the more remarkable because the distance between lens and retina is fixed, and the lens itself must change its shape. Now compare this with the focal adjustment of a camera. Here the lens remains unchanged, but the film itself is moved until it reaches a sharp focal image. The lens itself lies between two liquids. These liquids can exert pressure. All liquids cannot be compressed. You may ask then, how is this soft, pliable body of the lens made to take on the different degrees of convexity necessary for accommodation? In order to explain this, let us again call attention to the important ciliary muscle, which we see here in the diagram. This muscle is shaped like a broad ring which can expand and contract. Whenever it does contract, it must press upon the non-elastic vitreous humor. This liquid is confined within the rigid capsule of the eyeball and must, therefore, exert pressure upon the lens. Now, the lens as a whole cannot give way against the equally non-elastic aqueous humor and its confining cornea. So the only part which can possibly yield to the pressure of the vitreous humor, or body, is the soft substance of the lens. Whenever the image upon the retina becomes blurred, the brain automatically causes the ciliary muscle to contract or to relax until the lens has attained just the right shape to restore a sharply defined image upon the retina. This is the remaining portion of the choroid, called the iris, with its central opening, the pupil. Like the diaphragm of a camera, the iris regulates the amount of light and sharpens the image upon the retina. The iris acts automatically, and so is an important link in the process of accommodation. Its action is caused by two sets of delicate muscle fibers within the iris itself. These muscles are shown here in simplified diagram. These spoke-like radial fibers pull the pupil open. This ring-shaped muscle around the pupil closes it. In this side view, we see the opening and closing of the pupil, so that we may more clearly understand another important part played by the iris. It is well for us to know that our eyes are one of our greatest gifts of nature and are indeed worthy of our constant care and protection.